I'm going to do one more video on entropy. Maybe I'll do more in the future. But I thought I would at least right now do one more because I really want to make clear the idea of entropy as a macro state variable. So let me write that down. And S, which is entropy, is a macro state variable. I'm going to write macro in bold red. It's a macro state variable. And I want to emphasize this, and I talked a little bit about it in my previous video, but I think even then I wasn't as exact as I needed to be. And the reason why I want to say it's macro is because there's a very strong temptation to point to particular microstates and say, does this have higher entropy or lower entropy than another? For example, the classic one, even I did this. You know, you have actually let me make a bigger, thicker lines. Okay. So you have, say you have this box that has a divider in it. We've gone through this multiple times. Let me draw the divider like right there. Okay. So we say at first if we have a system where all of the molecules are over here. So that's our first scenario. And then our second scenario, we studied this a lot. We blow up the wall here. We blow up the wall here, and we actually calculated the entropy. Okay, let me copy it, and then I'm going to paste it. So let me put these next to each other. All right. So I have these two things, and then the second time I blew away this wall. Let me blow it away. Okay, let me erase the wall there. And then we said once the system reaches equilibrium again. Remember, for a system, these macro state variables like pressure, like volume, like temperature, like entropy are only defined once the system is in equilibrium. So once the system is in equilibrium again, you know, these particles are now, I want to do the same number of particles. So maybe let me erase some of these particles. Let me move them. Let me see if I can select some. So, whoops, no, let me see. I could select these particles, and I could move them there. So we'll have a more even, that's not a good way to do it. Let me just redraw. It said 1, 2, 3, 4, 5, 6, 7, 8 particles. Let me erase what I have. I'll make it with a more even distribution. So then, once I blow away the wall, I might have 1, 2, 3, 4, 5, 6, 7, 8. Now the reason why I'm doing all of this is because there's a temptation to say that this state, what I just drew you when I, made sure to blow these away and draw 8 more, I drew a micro state. This is a micro state. This is a micro state where I'm actually, anytime someone's actually drawing molecules for you, they're drawing a micro state. They're drawing a micro state. Now, I want to be very clear. This microstate does not have more entropy than this microstate. In fact, microstates, you don't have entropy. You can't even, entropy does not make sense. What you can say is a system, what you can say, and this time I'm going to draw it without the particles, that if I have a container that is this big, that contains, so it has some volume, so volume is equal to V1, its temperature is equal to T1, and it has 8 particles in it. This has some entropy associated with it. And what we can say is if we were to double the size of this container, which we did by blowing away that wall, now all of a sudden, our volume is equal to 2 times V1, if we say this is double. Our temperature is still equal to T1. We saw that a few videos ago. And we still have 8 molecules. All we can say is, because the entropy of this system is higher. So now entropy is higher. And I want to make this very clear because you never see it drawn this way. People always want to draw the actual molecules. But that confuses the issue. That when you draw actual molecules, you're showing a particular state. For example, this system, if we were to actually measure the microstate, it could be, there's a very, very infinitesimally small probability, but all of the molecules, all 8 molecules might be right there. I mean, it's almost, you could wait for the whole universe to come and go, and it might not happen, but there is some probability it happens. So you can't assign entropy to a particular state. All you can do is assign it to a particular system. I want to be clear about that. So even I talked about a clean and dirty room and all of that. clean versus dirty room, clean room, dirty room. And the point I was making is the entropy of a room is not dependent on its cleanliness or its dirtiness. In fact, you could kind of view these as each states of a room. But even more, these really aren't even states of the room, because when a room is clean or a room is static at a macro level, they're static. Or when they're if I have my books are lined like, let me see, sometimes people look at a deck of cards and say, oh, if I have all my cards stacked up like this, or if I have all my cards that are all messy like that, all messed up around, that this has higher entropy. And I want to make it very clear. I mean, maybe you can kind of make an analogy, but that's not the case. These are both of these systems are macro states. For example, I mean, these aren't like, it's not like these cards are vibrating around any more than these cards are. It's not like these can take on more configurations than these cards can. So when you talk about entropy, you're trying to take a macro variable that's describing at a micro level. And the cards themselves are not the micro level, because they're not vibrating around continuously due to some kinetic energy and whatever. It's the cards' molecules that are at the micro level. And if these cards, if you have the same mass of cards as you have here, and if they're at the same temperature, the molecules in these cards can take on just as many states as the molecules in these cards. So they're going to have the same entropy. Entropy is a macro state variable, or a macro state function, that describes the number of states a system can take on. So here, I would view the cards as a system. And what we care about is not the number of configurations the cards themselves can take on. The cards aren't constantly vibrating and changing from one thing to another. It's at the atomic level, at the molecular level, that as long as we are above absolute zero, and which we pretty much always are, things are going to be vibrating around continuously and continuously changing its state. So it's almost impossible to measure the state. And since it's impossible to measure the state, we use something like entropy to say, well, how many states can we have? And I mean, all of these things, entropy, whether we call it internal energy, whether we look at entropy, whether we look at pressure, volume, temperature, these are all, if you can think about it some way, these are shortcuts around having to actually measure what each molecule is doing. And entropy, you can kind of view it as a meta shortcut. I mean, temperature tells you average kinetic energy. This tells you all of the energy that's in it. This tells you, how frequently the molecules are bumping against a certain area. This tells you on average kind of where the outermost molecules are. Entropy is kind of you can almost view it as a meta state variable that tells you how many states, how many microstates can we take on. So I just want to make this very clear, because this is often confused, and there's a very, very, very strong temptation to point to a particular state and to say that that has higher entropy than another, that somehow this state is more entropic than that state. That's not the case. This system is more entropic than this system, than this half box. It has more volume. If they have the same temperature and the same if they have the same temperature and with more volume, then its particles can take on more possible scenarios at any given moment in time. Anyway, hopefully you found that a little bit useful. I just want to make it very, very, very clear, because this is often confused. This is a macro state variable for a system, where a system is composed of these things that are bumping around randomly every millionth of a second. They're changing state, so it's very hard to even measure one of the microstates. You can't point to a microstate and say, oh, this has higher entropy than another. Anyway, see you in the next video.